In this video, we're going to introduce the idea of the central limit theorem, but for proportions. So the scenario we want to talk about here is Chifaru wants to know what proportion of her friends like her favorite TV show. In this case, each friend has what's called a binary choice. They can either like the show, yes, or not like the show, which is going to be a no in this case. There's no in between. You're either a yes or a no. There's only two options. All right, for example, she asks 26 of her friends, and 17 of them like the show. The proportion is going to be 17 over 26. That's going to be the proportion of the yeses. But since it's a binary choice, it also tells her that 1 minus the proportion of yeses is going to be the no's, right? So that's going to be the proportion that does not like the show, the remaining 9 out of 26. So in terms of information, she really only needs to record the yeses to know what the no's are. If she knows one piece of this information, the other piece is the remaining part, right? The 1 minus. All right, so now some vocabulary and some symbols. We're going to use the symbol P for the proportion of the entire population that is a yes, right? So this is all of the people that we're interested in, right? So that's the proportion of the yeses in the entire population. And this proportion is going to be a number between 0 and 1. And the proportion of the no's is going to be 1 minus P. In our data set, we're going to let X be the symbol for the number of the sample that are yeses, right? So that would be the 17 of her friends that liked the shows. And the sample proportion of sample size n, that's 26 for our scenario, we're going to use the symbol P hat to be our sample proportions. Okay? Number of yeses over the total number in the sample. For example, for Chifaru, her P hat is going to be her 17 yeses over the 26 people she asks. So P hat for her is going to be 0.6538 or 65.38% if you prefer. All right, now I said this is going to be the central limit theorem for proportions. Remember, the central limit theorem told us that our data, our samples, come from a standard normal distribution. So this is going to be the conditions that we have a standard normal distribution. Okay? So we're going to let P hat be our sample proportion of sample size n. And furthermore, we're going to know population proportion P. Right? If the sample size times the proportion of the population that says yes is greater than 10, and our sample size times the proportion of the population that says no is also greater than 10, then our distribution is going to come from an approximately normal distribution, right? Our P hats are going to come from here with mean P and standard deviation equal to this thing. This is actually a significantly easier standard normal calculation than we had before. It's going to be the square root of the proportion of yeses times the proportion of no's divided by our sample size, right? And that's going to tell us our width. Right? And these conditions are a little different than the one we had last time. Previously, we only needed more than 30 data points. Here, we need that the number of yeses we can expect and the number of no's that we can expect have to be large enough, right? If either one of these is too small, right, then we're not going to capture enough in our sample to guarantee kind of the right shape, okay? So this is a little stricter of a condition, and we'll see what that means when we look at the calculation bit. Coming up in the next short video.